Today in the workshop, we'll take our AIY Voice Kit out of the box and put it on a breadboard. We'll set up the Google Cloud Speech API and learn how to control LEDs and motors just with our voice. We'll even build a voice-controlled traffic light. So there's a lot to talk about, so welcome to the workshop. Hey, welcome to the workshop and to the second video in our series on using the Google AIY Voice Kit. Now, for those of you who didn't see the first video, and I do recommend you do that, the AIY Voice Kit is a kit that includes a hat and some microphones, a push button, and a cardboard box. And by putting all of that together with a Raspberry Pi 3, we could create a device that can recognize our voice and respond to voice commands. Everything gets assembled into a cardboard box. We get to use the Google Cloud Console and the Google Assistant SDK, and once we're finished, we end up with a product that looks like this and can act like this. Okay, Google, what is the capital of Portugal?
Its capital is Lisbon.
Fascinating, I'm sure. Now, most of you will realize that you can also accomplish the same thing with any Android phone or any Android tablet. Or for that matter, you can buy a dedicated device like this little Google Home Mini. And economically, the Google Home Mini costs about the same amount of money as a Raspberry Pi 3 and a Google AIY Voice Kit. And of course, it comes ready to use right out of the box. So why would you buy the Voice Kit in the first place? Well, the answer, of course, is that the Voice Kit is not meant to replace a Google Home Mini. What the Voice Kit is for is to allow you to experiment with voice recognition and voice commands and add these onto your own project. And that is exactly what we are going to do today. I'm going to start by actually taking the Google AIY Voice Kit out of its box and placing it on the workbench so we can experiment with it more. We're then going to take a closer look at the hat, the hardware attached on top device that comes with the Voice Kit, because this is the key to interfacing external devices to it. We can drive things like LEDs and motors with it, and we can also take input from external sensors in order to read those sensors or to trigger the Voice Kit voice recognition itself. So follow along today as I take the Google AIY Voice Kit out of the box and start experimenting with it. Now, before we take a look at the hat and start experimenting with it, I'd like to clear up a few misconceptions that may exist about the hat. From the emails and comments I got after the last video, there are a few people who seem to be a little confused as to what the functionality of the Google AIY Voice HAT actually is. The Voice HAT itself does not process voice, it does not recognize voice, and it does not generate speech. What the hat is an interface. It takes the input from the microphones, filters it a little bit, I think, in order to get it down to just the voice range, and sends it up to the Google Cloud servers. On the cloud servers, there are functions that we can call through Google APIs, and the Raspberry Pi interfaces with these APIs. And when the Google API has processed the voice that we've delivered to it, it sends back the result. And then the hat's functionality is simply that of an audio amplifier. It amplifies it and sends it out to the speaker. Now, some of you may have had difficulty obtaining a Google AIY Voice Kit, and I want to let you know there are alternatives that you can use in order to perform these experiments. One of the alternatives that I've used before is by Seed Studio, and it's called a ReSpeaker, and I've got one over here. They make a series of these things. Now, this, as you can see, is a very, very small hat. It's actually called a Pi hat. And it's actually the same form factor as the Raspberry Pi Zero, but it has all of the functionality of the Google AIY hat. It's got two microphones on it over here, a jack for a speaker as well as jack for headphones. It's also got a connector to the GPIO, and it's got a connector for I2C. So if you cannot find a Google AIY Voice Kit locally, or if you can't order one where you live, you might take a look at getting a little device like this. This was under $20, so it's quite inexpensive, and its form factor also lends it to being used on the Pi Zero or Pi Zero W, which may be something that you'd appreciate because of the lower cost of those computers. So now that we've talked about the hat, let's take a closer look at it. The Google AIY Voice Kit hat, like any hat, has a connector to allow it to be connected to the Raspberry Pi. It uses the modern 40-pin connector, which is used with the Raspberry Pi 2, 3, and 0 models. There are two connectors we've already seen before: the 5-pin connector that connects to the microphone array, and a 4-pin connector that connects to the push button and LED assembly. Below these connectors are 4 connectors labeled drivers. These connectors can be used to drive external motors and LEDs and other devices. Along the bottom we see a second connector for a second speaker, plus a small jumper beside that. When this is shorted together, it allows you to use 2 channels of output to allow for stereo output. On the top left corner of the hat, we see an I2C or I2C connector. This allows you to connect the hat to sensors that use I2C as well as to other microcontrollers and microcomputers, so you can make a very sophisticated system with external Raspberry Pis and Arduinos connected to your device. It also supplies a 5-volt and 3.3-volt output. Next to that are 2 pins for receive and transmit. These provide serial communications capabilities. Beside that is a set of pins for the SPI or Serial Peripheral Interface Bus. This will allow you to connect devices such as SD cards and displays to your voice hat. It also provides a 3.3 and 5-volt connection. Below the I2C connector, we see a set of connectors that are labeled servos. These are 6 connectors specifically designed to be used with servo motors. Beside the servo connectors, we see an external power jumper. This jumper needs to be cut so that we can attach an external power supply to the board to allow it to have current to drive our external devices. Otherwise, it will try to power the devices with the 5-volt supply in the Raspberry Pi, which is not sufficient to power most motors and servos. And here are the connections for the external power supply. This is an external 5-volt supply with enough current to drive whatever it is you've connected to the voice hat. So here's my voice hat, to which I've soldered a number of connectors to make it easier to experiment with. Now, the most obvious one is this 2.1mm barrel jack. This is a power connector for the external 5-volt supply that's going to power things like servos and devices that are connected to the output driver. Now, in order to use external power, there is a jumper labeled JP1 that you need to slice down the center using a knife. I used an X-Acto knife to slice that, and I'll show you in a moment how you can test to make sure that you've got that slice correctly. Now, I've soldered 6 sets of connectors here for the servo motors. I've soldered some male header pins over here for the I2C connection, 2 pins here for the transmit and receive on the serial connection. The SPI connection, I've soldered 8 pins over here, and I've also soldered 4 sets of pins for the output drivers, and this will allow me to connect external devices to this board a lot easier. Now, as I said, you do need to slice this JP1 jumper, and after you do that, it's a good idea to check for continuity. So I've got a meter over here. When I touch the leads together, it makes that hideous sound. I'm going to check for continuity across it to make certain that I've sliced it. So I'll stick my meter on either side, and I do not get a sound. However, from this side, the side that is closest to the inside of the board, if I measure to a 5-volt test point, such as this one in the I2C bus, I do get continuity. So I can see I've actually sliced the jumper correctly, and I'm now going to be supplying power from an external 5-volt supply and not using the internal supply from the Raspberry Pi, which is limited in current. Okay, well this is what my AIY Voice Kit looks like right now. As you can see, I have removed it from the box, and I have placed it onto an experimenter's platform that I've built that I'll show you in a second, and I've got that here on my workbench right now. Now, if you decide to take your Raspberry Pi and Voice HAT out of the box to make it easier to experiment with, a couple of things you might want to note. First of all, you want to be very careful doing this. You might want to remove the micro SD card because it can catch on the side of the cardboard as you're taking it out of the box. Another thing you'll want to do is unplug the push button and the microphone connection because it makes it a lot easier to get those components out, and this way you can get the push button out without having to take the wires that you've connected to the push button, and it makes it a lot easier to put everything back together. So now let me give you a peek at my little experimenter's platform that I've built to experiment with the Voice Kit. Now, some of you may find this little setup of mine to be a bit extreme, and I'll be the first to admit that you're probably correct. Keep in mind, though, that I'm planning on using this not only with the AIY Voice Kit, but with a number of other Raspberry Pi experiments. So I wanted a Raspberry Pi experimenter's platform. I've added some solderless breadboards and a device called a T-cobbler, and this lets me get access to all 40 pins of the Raspberry Pi GPIO and bring them out for experimenting on the solderless breadboard. It's connected through a ribbon cable. Inside here, which I know you can't really see too well, I've got a little circuit board that connects two different 40-pin connectors onto it. I've put a right-angled 40-pin connector onto it for my T-cobbler, and I've used a long lead 40-pin connector so that I can stack a hat on top of this, similar to the way that you can sometimes stack shields in an Arduino, if you're familiar with that. So here, of course, is my Google Voice HAT with all of my connectors soldered onto it. I've put a little stand over here to hold the microphone, and I've also put a little stand over here with a board in which I've mounted the push button and the speaker. And so I've got a permanent arrangement right now that I can use for experimenting with the Google AIY Voice Kit, and as I said, a number of other Raspberry Pi devices as well. So now that you've seen my wonderful experimenter's platform, let's get on to doing some experiments. Before we begin working with the Google Cloud Speech API, there are a couple of things that you need to know. The first is that I filmed the first video in this series in December of 2017, and I used what was at the time the latest build of Raspbian for AIY on my Raspberry Pi. Since then, Google has created a new build of Raspbian for AIY, and I'm using that in these experiments. If you're using the old one, they'll probably work, but I can't guarantee that because I'm using the newest version of it. Now, in order to use the new version, what I did is I copied the assistant.json file that we created in the first video. I copied mine onto a network storage device, and then once I had my new build up and working it on the network, I just copied it back into the root of my home directory, which is the Pi directory. You could also use a USB memory stick if you wish to copy the file if you don't have a network storage device or don't want to use your network. It might be easier. After doing it, though, I noticed that there was one major change in this build, and that is that the files are in different locations than they were in the original one. Now, the reason for that is that this build includes not only the AIY Voice Kit, but also the new AIY Vision Kit, and they've put the files into different directories. And so when you go to run the examples, if you're using the examples from the original video and copy the file paths, they will not work. Now, I've updated the article, the original one, on the website to reflect these changes. I want to show you those changes right now. So let's move over to the AIY desktop. Now, here on the desktop, I'll just open up a file manager. And I'll make that big so you can see it. Now, it opens up in my home directory, which is Pi, and you'll notice here is the assistant.json file that I created. Now, AIY projects-python is where the dev terminal is going to open up. This is the root, and normally we would have just typed in src and then the name of the demo we want to run. But if you look in the src folder, you'll notice there aren't any demos in there. There's a folder in there called examples, and under examples you'll see one for vision and one for voice. If you go into voice, you will find the demo files. So let me illustrate that with the dev terminal. We can minimize that for now. Start the dev terminal, and I've made the font big on this so hopefully you can see it a bit better. And so let's just run the assistant library demo. Now you'll notice the path is now src examples voice and then the name of the file. It used to just be src and the name of the file. So once you put the correct path in, we can run our demo. And I can say, okay Google, how are you doing?
I'm feeling pretty chill. Since the weather is cooling down in many parts of the country, it's a good time to stay warm indoors and dig up some fun winter facts. I learned that the record for the largest snowflake is 15 inches wide and 8 inches thick.
And I find that pretty fascinating, not only the size of the snowflake, but for the fact that someone actually has measured all the snowflakes and knows that that's the biggest one. But snowflakes aside, you can see that the demo works just as long as you change the path. So if you're following the original instructions, or if you're still using the original build, you will have to change the paths and everything I'm doing in order to follow along. Having said that, there's a couple of other things I wanted to mention before we start working with the Google Cloud Speech API. Now, one thing is that the Cloud Speech API is going to require you to set up a billing account. This is because Google actually charges for using this. Now, before you panic, Google will give you $300 worth of credit, and that's way, way more than you're going to need to do all these experiments. So you won't actually get charged anything, but you're going to need to have a valid payment method, and the payment method will vary depending upon which country you're in. And speaking of that, if you happen to be European, you may find that you need to set up a business account and not a personal account in order to use the Cloud Speech API. It is not available in some European countries under personal accounts. So hopefully neither of those things are going to prevent you from doing the following experiments. So now that we've taken care of all of that, let's go and install the Cloud Speech API. So I've opened up my web browser and I've gone to the Google Cloud Console at console.cloud.google.com. You may want to bookmark this because you'll be going here often. And to bookmark in the web browser, just hit this little star over here and you can write whatever you want. I'm going to call it Cow Console. I'm going to keep it on my bookmarks bar. Okay. Now the first thing you want to do is make sure you're working with the correct project. If you only have one project, then you've got no problem. By default you are. There's a menu up over here, and I'm actually in the correct project now, but if I wasn't, I would just click it to get a little box that pops up, and I could select the project that I wanted to use. But as I said, New Voice Project is the one I worked with before, so I'm already in the correct project. Now, as I mentioned, you are going to need to set up billing in order to perform the experiments that we're going to do. So we might as well take care of that right now. So go into the menu by clicking this icon here, and then go down to billing. Now, right now you'll see the project has no billing account. You can either link a billing account if you have an existing one, or manage billing accounts. Now, I have an existing account, but there's a good chance you don't. So you'll go into Manage Billing Accounts, and from there you'll be prompted to set up a new billing account. You'll go through all the prompts to enter all of your payment information, and once that's done, you can return to this screen. I'm going to link a billing account to this project. Okay, so I only have one billing account over here. I'm going to set the account. and it tells me the amount I have left. Incidentally, I'm in Canada, so this is in Canadian dollars, and that's the equivalent currently of 300 US dollars. Okay, now that I've done that, I can go back into my menu. I'm going to go to APIs and Services, and I'm going to go into Credentials. Now you might remember from the first experiments we've done this before. We're going to create a new credential, though. This is going to be a bit different than the last time. We're going to go into Create Credentials, and we're going to create a service account key. Now, this select menu right now will only have one thing in it, New Service Account. So I'm going to select that. And as I do, it's going to pop up some things where I can name my service account. Now you can give this any name you want. And I'm going to call this my AIY Services, and it'll give it a name down here. Now I'm going to select a role for it. And the role is going to be Project and is Viewer. Now I'm going to leave this as JSON. I'm going to hit Create. And it has saved a private key to my computer. And I'll close this dialog box. Now once again, this private key came with a very long name. I'm going to need to rename this in order to do the experiments. Let's just minimize the browser for a moment. And we'll open up the File Manager. We go into Downloads. I'll find my key. I'm going to right click on that and I'm going to rename it. I'm going to call it cloud_speech.json. Now this is case sensitive. You have to name it exactly this. And once again, I'm going to take a copy of that key. I'm going to go in my root directory and I'm going to paste it. So I now have a second JSON file called cloud_speech.json. Can now close the File Explorer and go back into the Cloud Console. I'm going to hit my menu again, APIs and Services. I'm going to go into the library. Now I'm going to need to find the Cloud Speech API, so let's just look for speech. And there it is, the Cloud Speech API. I'm going to select that. And it tells me some details about the Cloud Speech API, which I'm now going to click Enable. It's going to tell me that billing is required for this, and I will enable billing. And this completes what I need to do in the Google Cloud Console at the moment. Now I can close the Cloud Console or just minimize it, which I'll do. I'm going to hit the Check Cloud icon here. And it tells me that everything is set up and ready to use the Google Cloud, and I can hit Enter to close this. And so now we're ready to begin our experiments. Now that we've set up the Cloud Speech API and confirmed that it is working, we can test it out using one of the sample scripts that Google has provided. We'll start the dev terminal. And this is the script we're going to run. It's cloudspeech_demo.py. So the full path is src examples voice cloudspeech_demo.py. Now this demo will control the LED on the push button. And it's initiated by pushing the button, so it doesn't respond to the OK Google command. Instead, it is triggered by the push button. And there's a couple of commands we can give it. I push the button, and I'll say, turn on the light. Now you'll notice there's a brief delay from when I said turn on the light until when the light actually came on. And that delay is because it actually has to take my voice, send it up to the cloud, process it, and send it back. So there is a bit of a latency period. And every time I want to give it a command, I need to press the button again. So I can say, turn off the light. I can also blink. Turn off the light. Now you'll notice in the dev terminal window that every time I speak, it actually prints out what it is I said. And we'll be using this fact in some of our scripts later on. You can also close the script by speaking to it. I'll press the button, and I'll say goodbye. And you'll notice now we are back at the command prompt. Our last demonstration illustrated the principles of working with voice recognition. We provided a trigger by pushing the button, and then after the trigger, the system started listening for commands that it was already waiting to hear. Once it heard one of those commands, it sent the commands up to Google's cloud server, it processed it up there, and in turn came back and then performed the action. So we pressed a button and we said turn on the light. And after a brief delay, it turned on the light. We pressed the button again and said turn off the light, and it did the same. Now as a practical circuit, it really isn't anything. I mean, after all, I could just wire a button up to a light, not even use a Raspberry Pi, not have to go up to the internet, and immediately turn the light on and off. So practically speaking, it's not a very practical method. But it does illustrate one thing about voice recognition systems, and that is that you need to have a trigger. Now, the trigger can be an action like pushing a button or activating a motion sensor, or an external software trigger when an event occurs, say a time has elapsed or something, which then has the voice system listening for a command. And that principle is true for all voice recognition systems, be it Amazon's Alexa system, or the Siri from Apple, or Google's voice command system. Now, the other trigger, of course, that we are used to is being able to say a wake word, like OK Google. And I think for most of us, that's the way we really want our voice recognition to work. Rather than having to push a button and say something, we'd rather just say, OK Google, turn on the light, or OK Google, turn on the television, and have it react to that. And so in our next demonstration, we're going to do exactly that. The demonstration we're going to look at is another one of the sample demonstrations that Google has included with the AIY Voice Kit. This is called the Assistant Library with Local Commands demo. And we're going to take this demo, run it, and then we're going to modify it to control our own devices with it. So before we run it, let's take a look at some of the code that's going to be used. Now, this code, as it says at the top, is licensed with the Apache license. And if you go and read the terms of the license, and they give you a link over here where you can go and see the terms of the license, you'll find that you're free to reuse this license, to modify it as you wish. But if you do modify it, you need to leave the license agreement in, and you have to put a little line in there saying that you're the one who's modified it. So we are going to be doing that to the code that we modify after looking at this code. Now this code can run the voice recognizer by simply using the OK Google trigger, and then it'll respond to it. And there's a lot of code here. Now we're not going to go over all of it because it would be too complex to do in this video, but there are some key things you should know. Now first of all, it starts off by importing a number of libraries which will be necessary in order to use Google's Voice API. Then after that, what I really want to show you about the code is these functions that are defined at the top. Now this code can do three things. It can power off your Raspberry Pi, it can reboot your Raspberry Pi, or it can read you out your local IP address. And for each one of those functions, they've defined a function. So we've defined a function called power off Pi. And in that function, the first thing we do is we use an AIY audio say command. Now that will cause the voice recognizer system to say something. So in this case, it says goodbye. Then after that, we run the actual command we want to. So this is just a command to shut down our system. Now we also have a function called reboot Pi, and it works in a similar fashion. We use an AIY audio say, it says see you in a bit, and then we will go and run a function to actually reboot our Raspberry Pi. And the third one is say IP, one that says your IP address. Now in this function, first we run some code to actually find out what the IP address is, and then we use an audio say command to say my IP address is, and then it reads out your IP address. So keep that in mind. We've defined three functions over here. Now we're going to go further down into the code, and it's down into these else-if statements over here that I want you to pay attention. This is where we are looking for actual words that are spoken. So we're assigning this to a variable called text. So if the text equals power off, we first of all stop the conversation. We use assistant stop conversation. We do that every time. And then we call a function. And this function is power off Pi, which is the function that we defined here. So basically, when someone says power off, if the text says power off, then we'll go and run the power off Pi function. If someone says reboot, then we'll go and do the reboot Pi function. And if you say IP address, it'll again stop the conversation and run up and run the function for say IP, which says your IP address out to you. And again, I'm not going to go through all the elements of this code. It calls other libraries, etc. If you wish to, you can go through the libraries it calls and really understand it. But for now, let's just try running the code. So let's minimize this and open up our dev terminal. And in our dev terminal, we'll run the assistant library with local commands demo. So there's the whole pass, src examples, voice, assistant library with local commands demo.py. We're going to run it. And as it says, we just have to say, OK, Google, and speak. So, now if I say a normal command, you'll notice it comes back in the normal fashion. So, OK, Google, what time is it?
It's 6:02.
And you'll notice the standard response that we're used to. And also on the screen, it prints out what we said. I said, what time is it? Now, let's use one of the commands we just built in. OK, Google, IP address.
My IP address is 192.168.1.106.
And that seems to work. And we can Control C to get out of this. Now you probably noticed that the voice sounds different. It is not the same Google lady that we're familiar with, but it's more of a voice synthesizer sound that we get back. And this is true of all of these custom bits of code that we can write. But we can now use this code that we've seen to write our own code to control some devices. And let's do that right now. Now for the next demonstration, I thought we'd have a little bit of fun. So what I've done is I've created a voice-controlled traffic light. And in order to do that, I've built a traffic light with 3 LEDs on my breadboard. As you can see, I've wired some LEDs up. I've got a red LED, a yellow LED, and a green LED, which of course represent the 3 lights on a traffic light. Now you could, if you wished, use opto-isolators, drive a relay, and drive a real traffic light with this, although I would advise against driving a traffic light on your street, because I'm sure your city probably has bylaws that prevent you doing it, even though it would be really cool to be able to talk to the traffic light and set it green whenever you wanted to. You'd get to work a lot faster that way, I'm sure. But anyway, let me show you how I've hooked the LEDs up to the voice hat. I've taken the red LED and I've hooked its cathode to ground. Its anode is connected to a 330 ohm dropping resistor, and I've connected that to the servo 0 connection on the voice hat. This is actually connected to GPIO pin 26. The yellow LED also has its cathode connected to ground and its anode connected to a dropping resistor, and it goes to the next servo pin, servo 1, which is internally connected to GPIO pin 6. And then the green LED, again I've grounded the cathode, put the anode connected to a dropping resistor, and connected it to servo 2, which is GPIO pin 13. So now that you've seen how this is all connected, let's take a look how I've modified the code we just looked at in order to drive my traffic light. So here's the code that we're going to be using to control our traffic light. Now again, this is based upon the same code that we looked at last time, and so I'm just going to show you the things that I've modified in order to drive my traffic light. Now, because this is under the same Apache license, I've added a couple of lines here basically saying that I have modified the code. Now we'll go into the code. The beginning here is of course identical to the last code. And now we have some statements that I've added myself. I've imported the GPIO library and called it GPIO. And then I've set up the GPIO pins. Now first of all, I've done set mode GPIO BCM. What BCM means is it uses the Broadcom control pins, and these are the standard numbers we use for GPIO pins in the Raspberry Pi. You can also say GPIO board, and if you did that, you'd be talking about the physical pin numbers on the 40-pin GPIO connection, which are not the same as the Broadcom numbers. But it is typical to use the Broadcom numbers, so I've set mode to Broadcom with this BCM command. Now set warnings false just suppresses any warnings that are going to go to the console when I'm running this code. You can take this line out if you want, and you'll see a number of warnings about these pins already been in use, so it's up to you whether you want to include this line. I just thought it ran a little cleaner with it. Then I've defined 3 of my GPIO pins. GPIO pin 26, pin 6, and 13 are all defined as outputs. And GPIO pin 26 corresponds to servo 0, pin 6 corresponds to servo 1, and pin 2 corresponds to the servo 2 output. And so 26 has been hooked up to my red LED, 6 to my yellow LED, and 13 to the green LED. Now, as you recall from the last code, the way we do this is we define a function, and then later on in the code we call up that function. So I've defined a number of functions here. Let's take a look at the first one. It's called red LED on. Now first of all, I use an AIY audio say to basically say the red light on. Now you could type something else inside there if you want. Red light is on. I've turned the red light on. Here is the red light. Whatever you'd like to hear it say back to you. And then I've set output 26, which is connected to that red light, to true. That brings it high and turns the LED on. Now red LED off is practically identical, except of course I'm saying red light off, and I'm taking the output and sending it false to turn the light off. I do the same for the yellow LED and the green LED. So I've got 3 functions that turn the LEDs on and off. Then I've got another function that turns all of the LEDs on. So I say turning all lights on, and I set all 3 of those outputs to true. And then all LEDs off, turning all lights off, set those outputs to false. And here's my traffic light functions. Traffic go should only turn the green light on. So I'm going to say green light, you can go. I turn the red and yellow lights off, and I turn the green one on. the traffic is stop, I say red light, you must stop. I turn the red light on, the red LED, and then the yellow and the green LEDs are turned off. And then if I have a traffic caution over here, I say yellow light, be careful. I turn the red off, the yellow on, and the green off. Okay, and then these are the same functions that came originally with the code, the power off, reboot, and say the IP. I did not remove them from the code, but you could if you want. Now back over here we have all these else-if statements, and these statements basically are just listening for you to say specific text so it can run those functions. And so here we have the red light on. So if you say red light on, I stop the conversation and then call the function I wrote to turn the red LED on. The same for red light off. I'll call the function for red LED off. And the same thing here. For my traffic, I have traffic go. So if I say traffic go, I call the traffic go function. Traffic stop, I call the traffic stop. And traffic caution, I call the traffic caution function, etc., etc. So that calls all the functions I've defined up at the top. So now that you have seen the code, let's take a look at it in action. So I've loaded the code and we're ready to begin our demonstration. Okay, Google, red light on.
Red light on.
Okay, Google, green light on.
Green light on.
Okay, Google, all lights off.
Turning all lights off.
Okay, Google, all lights on.
Turning all lights on.
Okay, Google, traffic go.
Green light. You can go.
Okay, Google, traffic stop.
Red light. You must stop.
Okay, Google, traffic caution.
Yellow light. Be careful.
And as you can see, this seems to work perfectly. Now for the next demonstration, I'm going to control a small DC motor with the voice hat. Now I want to show you how I wrote the code, and I'll do that in a moment. The code's actually fairly simple. It's fairly similar to what we worked with controlling the traffic light. But I want to talk about a couple of problems I ran into while designing this, and they have to do with noise. Noise of two types. The first type of noise is electrical noise. DC motors actually generate a fair bit of electrical noise when their brushes are making and losing contact. And in order to suppress that noise, I soldered a small capacitor right across the terminals of my DC motor. I used a 100 nanofarad capacitor. You could use something in that range, and it should help suppress the noise. Another type of noise I ran into, however, was the actual noise of the motor itself, the audible noise. If it's too close to my microphones, it's so loud that the mics can't actually hear my voice commands. So that's another consideration you have to make. Now I've mounted my motor on a little stand and brought it far enough away so hopefully the microphones over here aren't going to be affected by it. I've also twisted the wire, as you'll notice, and that is an additional way of suppressing electrical noise. If you wanted to do this permanently, I would suggest doing things like putting shielded cable onto the line going to the microphone connections. Putting the whole thing into a metal shielded box would probably help, with a couple of terminals to connect the motor, and keeping that capacitor onto the motor. Now here's how I've hooked everything up. The hookup is very simple. I've soldered a capacitor across my motor, and I've connected the two leads of the motor to two of the pins on the driver 0 chip. Now, one of the pins, the side pin over here, is the ground pin. The center pin of the driver 0 chip is actually connected to GPIO pin 4 through a transistor. There's also a diode in there, and this prevents the reverse EMF from the motor from damaging the board. I've also left my LEDs from the previous hookup in the circuit. Now because I've left the LEDs in there, I've decided to use them in the code as well. So now let's take a look at the code I'm using to drive my motor. So once again, our code is based around the Google library with local commands example. I've kept all the licensing agreement, and I've added a few lines about my own modifications to it. And we start off exactly the same way as the code originally did, so we won't go through that. Once again, I'm importing the GPIO library, and this is to drive those LEDs that I still have connected. I'm also from the GPIO0 library importing the PWM output device library. Now this is a method of controlling devices with pulse width modulation, which is how I'm going to be controlling my motor. If you are not familiar with pulse width modulation, I would suggest you take a look at my video on the L298NH bridge, because I explain pulse width modulation in detail in that video. Essentially, this is a way of sending pulses in order to control things like motors and LEDs. Now, the next few lines are the same as what we saw in the last bit of code. I'm setting up the GPIO to the Broadcom control mode. I'm suppressing all the warnings and taking the 3 GPIO pins for the LEDs and once again setting them up as outputs. I then define an object that I call motor1, and it's a PWM output device connected to GPIO pin 4, which is the same as the driver 0 pins that I've connected my motor to. Now once again, I've defined a number of different functions. Now I've defined 3 of them actually. Motor on full is my first function. So I use an AIY audio say command, and I just say motor on full speed. You can say whatever you'd like to say. Then I set the motor1 value parameter to a value of 1. Now by setting it that way, that will turn the motor on full speed. It tells the pulse width modulation to just take everything and send it full out. And then my GPIO outputs, which are the same as they were in the last sketch. I'm setting the red light off with a false, the yellow light off with a false, and the green light on for true. So when my motor comes on full speed, the green light will come on. Then I define motor off, which is essentially the same thing. I say motor off. This time I set the value of the motor 1 to 0, and that will set everything off. There will be no pulses at all going to the motor. And now I'm going to set my red light on, my yellow light off, and my green light off. So the red light will come on when the motor is turned off. And then I've defined a third function called motor on half. And the audio is going to say motor on half speed. And I set my motor value to 0.5. Now you can use any value between 0 and 1 to control your motor, so you could define a number of functions for various different increments of speed in your motor. I just chose to choose 3 of them, off, half, and full, for this demonstration. And again, I'll control my lights. I'm turning off the red light, I'll turn on the yellow light, and turn off the green one. So when I tell it to go half speed, the motor will go half speed, and the yellow light will come on. Now once again down, I have a number of these elif statements, and they basically interpret the voice I'm saying and call the correct function. So if I say motor on, it's going to call the motor on full function that I just described to you a few seconds ago. If I say motor off, it'll call the motor off function. And if I say motor half, it'll call the motor on half function. And again, you can add functions and interpretations as much as you want to granularly control the speed of your motor. So now that you have seen the code, let's run the code and control our motor. So my code is running in the dev terminal. I've got power hooked up to the board, and I'm ready to control my motor. Okay, Google, motor half.
Motor on. Half speed.
Okay, Google, motor on.
Motor on. Full speed.
You'll notice the distortion it picks up from the motor noise. Okay, Google, motor off.
Motor off.
And there you have it. Now, one thing I need to mention about using the Google Cloud Speech API, as you saw earlier, you need to set up a billing account in order to use these services, but you won't be charged. You get $300 worth of credit that's valid for a year. But one thing about the credit is that it is parceled out monthly, and you get an hour's worth of time on the Cloud Speech API or any of the other billable APIs before you're actually charged. Now, to give you a rough idea of how much you're going to consume, I looked at my Cloud Console before I filmed this, and I've consumed a grand total of 33 requests to the Cloud Speech API. And that includes the requests I made while I was setting up the experiments that I've showed you in the video. So my consumption is nowhere near the 60 minutes that I'm going to require in a month. In fact, it's pretty well about a minute or so. So you'll probably never see a charge from Google. If you do, they will warn you about it before you are charged to give you an opportunity not to use the Cloud Speech API until it rolls over to the next month. And the charge is very, very minimal. And you can look in your Cloud Console to see your consumption rate. Well, that about wraps it up for today's video, but it certainly doesn't wrap things up for the AIY Voice Kit. There is so much potential with this kit that I'm going to be doing another video on the Voice Kit, so you can look for that coming out very soon. Now, the best way to find out about new videos is to subscribe to the channel, so if you haven't subscribed to the channel, please do so. I would really appreciate that. Until then, please take care of yourselves, and I hope to see you again soon here in the workshop. Goodbye for now.